There we go. Let's begin again here. So lemma 2.4, we have A, B, C points in topological space, and we have paths from A to B, and alpha naught and alpha 1 are two paths from A to B, right? And beta naught and beta 1 are two paths from B to C, such that they're both, they're each homotopic, right? Like alpha 0 is homotopic to alpha 1, beta 0 is homotopic to beta 1. Then the lemma 2.4 says that the product of alpha naught beta naught is equal to, well, not that they're equal, but they're homotopic, right? So if you join homotopic paths, then that would be homotopic to if you picked a different representative, right? Like, so it's saying that in my picture, in the previous, let me just draw a picture of what this lemma is saying. It's saying if you have so here's like alpha 0, alpha 1. I usually draw the other, my picture, I guess, I put alpha 1 upstairs, right? And then you have beta 1, beta 0, right? Here's your A, your B, your C. Then it's saying, if you look at the path alpha 1, beta 1, which would be like this one, right? It's saying that that is homotopic to the join of these two guys, right? So you think you can use it as a tool to kind of break paths down into fundamental pieces? I think that that might be a reasonable intuition. Okay, so that's lemma 2.4, which I will not prove. Lemma 2.5. I want to get to the punchline today. Lemma 2.5, if we have alpha and beta and gamma paths, well, he defines well anyway alpha. I'm not sure if I don't know. I'm debating whether or not I need to define this, or if this is. I think this is just a derived. Forget the lemma for a second here. Alpha beta gamma of S, right? I guess this is the join of two. Alpha beta is a path, and then we're taking that path and we're joining with gamma. So we can still just use the definition of join that I already gave, right? And what he says is if you flesh this out, you get these three cases, right? You get alpha of 4s, is what he says. You get alpha of 4s. You get beta of 4s minus 1. You get gamma of 2s minus 1. And that's for 0 less than or equal to s less than or equal to a fourth. 1/4 less than or equal to s less than or equal to a half, 1/2 less than or equal to s less than or equal to 1. In contrast, if you look at alpha, beta, gamma, like this, of s, you get a different thing. You get alpha of 2s, 0 less than or equal to s less than or equal to 1/2, beta of 4s minus 2, 1/2 less than or equal to s less than or equal to, I think, 3/4. Yeah. And then gamma of 4s minus 3 for 3/4 less than or equal to s less than or equal to 1. All right. So there's no reason that these have to be equal. Yeah, I mean, they don't have to be the same path. Yeah, I mean, they don't have to literally be equal. Because they've got different. I mean, right. So I do think it's clear already that they're covering the same set of points in X, right? They're covering the same set of points, but they're covering it at different parts at different speeds, right? So, like, whichever one's in the outside gets double speed, whichever one's in the inside gets quadruple speed, right? Because it gets double the double. Double's quadruple. So that's why alpha beta here have quadruple speed, whereas beta gamma here have quadruple speed. But if you think about it for a second, it's just the same set of points, right? So yeah, they're not equal, but it's not at all surprising that we do have the following theorem, which is that alpha beta gamma, I'm going to write it this way, is equal to alpha beta gamma. So that's lemma 2.5. It follows from the reparameterization lemma, because that's what these maps are, just reparameterizations of one another. And as such, they're homotopic. Yeah. So that's interesting. We do get associativity of the product of homotopy classes, even though we don't have associativity of the paths themselves. We gain associativity at the level of homotopy classes, which is kind of cool. And then what else? He defines constant. What's a constant path? Come on. So what would a constant path be? Constant path at A is gamma of S equals to A. I mean, it's just dumb, okay? But here's what's not dumb. We write gamma equals to A for this. Why is this meaning? I mean, it's okay. So this is important because then that gives us a way of joining constant paths to given paths, right? So like the next lemma, which I forgot the number of. Come on. Lemma 2.6. Lemma 2.6. It says that if you have gamma path from A to B, all right, then A gamma is equivalent to gamma is equivalent to gamma B. Or better yet, let's use notation. I'll let you read the proof. It's not profound. All right, so we can join a constant path to a given path and not change anything. Finally, definition. If alpha is path from A to B, then alpha inverse is path from B to A, given by alpha inverse of S equals to alpha of 1 minus S. So that's the reversal of the path, right? So he says alpha inverse corresponds to running backwards along alpha. Although, for example, the constant paths, like A inverse is equal to A, I think, or, well, wait a minute. He says, in particular, for the constant path B, we have B inverse equals to B. Okay, great. Lemma. If alpha 0 is equal to, if alpha 0 is homotopic to alpha 1, then guess what? Alpha 0 inverse is homotopic to alpha 1 inverse. So this notion of reversal plays well with homotopy classes. So if we have two paths that are homotopic, then their reversals are likewise homotopic. Of course, the paths are homotopic from A to B. The reversals are homotopic from B to A. And all of this means we can define the inverse of a homotopy class, right? So what's the inverse of a homotopy class? I mean, we can give meaning, definition, right? Gamma inverse is equal to that. So for, given path gamma from A to B, we define gamma inverse from B to A and then his lemma 2.8, it says let alpha be a path from A to B. Let alpha inverse, well, I guess I shouldn't draw it differently, but the other way, alpha inverse be the path from B to A, right? Then if we look at the homotopy class of alpha times the homotopy class of alpha inverse, that's equal to the constant path at A. Does that make sense? I mean, so to break it down, this is alpha inverse, right? Which is alpha inverse. But if you take the path in its reversal, you go from A to B and then B to A, you just stay at A. So this is just A. It's like before and after class. If you could somehow hopefully we don't go back to where we started. I mean, well, anyway. Okay, so listen, I know you don't know you haven't had a class where a group has been defined yet, right? But yeah. So this is the definition. Pi 1 of xb is the fundamental group of x based at b. And this pi 1 of x, what is it? This is the set of homotopy classes of what? Loops at B. So for the next section, we basically look at A equals to B. In that case, it's a loop. But everything we've done today doesn't need that A and B are distinct. And in fact, if A and B aren't distinct, right, if we'll look at paths that begin and end at B, loops, we can talk about the homotopy of loops, because that's just a special case of the homotopy of paths with fixed endpoints. We're just saying the fixed endpoints are equal in B. And theorem 3.1 says that the set of homotopy classes of loops based at B with the operation of multiplication of homotopy classes is a group. The proof of that's already on the board, because we have seen that that group operation is what? It's associative. So a group is an abstract set with a multiplication. Here the multiplication is joining homotopy classes. So we've proved that that operation is well defined because it's independent of the representative of the curve. It doesn't matter which representative of the homotopy class. What's that? It's over there? Oh, over here. So here, this proves that the multiplication of homotopy classes is well defined. So the group operation is closed. Well, not closed, but it at least makes sense. Although I suppose it also shows it's closed because if you take two paths in X, you get another path in X, and hence we get a new homotopy. Our homotopy class is again a homotopy class of a path. The thing that I haven't sorted through the details yet is like, why is it true that if you take loops and loops of loops of loops, why if you join loops do you get loops? But it's not hard to see that if you take a loop and put it to a loop, take a loop and join it to a loop, you still have a loop. Because if you begin and end at the same point, you always, it's not complicated to see that we preserve loops. We need that. Anyway, what we've gone through this class is already proving that the operation on homotopy classes by joining paths and looking at their homotopy class is in fact a group operation, because we have an inverse for every homotopy class from the homotopy class of the reversal, and we have associativity of the homotopy class joining. And what else? What about the identity? What's the identity? What's the identity in the fundamental group based at B? In other words, what? Yeah, it's just B. So like B times gamma is equal to gamma for all loops. And I'm nearly done. I just wanted to say one more thing. So this is the fundamental group of X based at B, and he says, if the fundamental group consists only of the identity, right? If that's it, if B is the only thing if pi1 x b is just the set containing the stupid, if it's just that, if that's the only thing in there, then that's said to be a trivial fundamental group. In that case, it's traditional to just say this is equal to 0. All right? And an abelian group, yeah. He says 0. I mean, it's what in Gamelin, but I think it's pretty common to call it 0. Oh, well, let me tell you some things. One thing we've already proved, the thing I erased earlier that we proved that any two paths in a convex subset of Rn were what? Homotopic, which means that any two loops in a convex subset of Rn are homotopic, which is to say that the fundamental group for a convex subset of Rn is trivial. If I have a what? If you have groups that goes through the same points multiple paths. Right. Right. So, okay, so just to give you, I mean, I won't prove this today, but if you take the punctured plane, right? You could take this loop, take that base point B, right? Then here's one loop. It would be homotopic to this loop as well, right? But this is my base point B. I just picked one, okay? But neither of those are homotopic to this. Because I can't, there's a hole. And so this is actually tied to the connection that the fundamental group of the circle based at 1 is the integers. We'll spend about an hour proving that. We'll spend a while. It'll take us some time to actually derive that. It's not obvious why that, well, maybe it is, but it depends what kind of intuition you have for what we're doing. I don't know. But, and so here's the definition. A space X is simply connected if its fundamental group is trivial. To make sense of that, it has to be a path-connected space. If the space is path-connected, we'll prove next time that the fundamental group doesn't depend on the base point. You can transport loops from one point to another. So with that in mind, the fundamental group for a space can be defined independent of the point. And in that context, a space is said to be simply connected if its fundamental group is trivial. For example, a convex subset of Rn is simply connected because it has trivial fundamental group. This makes rigorous this vague comment that we make in Calculus 3 about what simply connected means. Simply connected is a statement about deforming loops to a point. Connected is, does there exist a separation, you know? But anyway, that's where we're going. This is, of course, the start of algebraic topology. Algebraic topology is when we use abstract algebra to gain insight into topology and vice versa. For us, mostly using algebra to gain insight into topology. But don't worry, it doesn't really require deep group theory. I mean, he has a 2-page, 3-page introduction to group theory that actually has everything you need for what we're doing. So it's not bad. And we won't go that deep into algebraic topology, just a little bit of homotopy theory.